Welcome all of you for today's session. This is the 12th live session for economic operations and control of power system. And after this, we'll be having one last session on Saturday. The timing will be shared with you in the announcement section. And we will wind up in that session by going through all the week's content. Mostly, we will only discuss the questions so that you can prepare yourself for the exam. And if you have any kind of doubt till now in the entire course, you can ask there in the last week, which is a Saturday, the summary or you can say wind up session for this NPTEL course. That will be the last session. So that will be the last session for this course. Let us move ahead. We'll go through the overview of week 12. And we will start. We'll have some. If you have any doubt also, then we can take your doubts also. Let us begin today's session then. So just to remind you, the deadline for assignment 12 is October 16th, which is tomorrow. Please submit the assignment on time. This time assignment is also not that difficult. It is easy. And all of you have been already accessing the video for live sessions as well as the PPTs and PDF used here for the live sessions. So you can use them using this link. And then before moving on to the summary of week 12, what we are going to do is we'll see the question 8 of the week 11 assignment. There was some doubt regarding this, and I'm sorry, in the last week I missed one point, that we have to respect the limits of generation also. So that I missed somehow in the last session, so sorry for that. And we will cover that thing here. And one student has asked me a question also regarding this 8th question, so that also we will discuss today. So the question was that the two generators A and B, which have droop of 4% and 5%, they are rated at 200 and 300 respectively, and they are operating in parallel. When they want to serve a total load of 500, the ratio of load shared by generator A and B would be equal to. Yes, there is this no load frequency is same here, but droops are different. And because droops are different, they will share different load. If droops are same, they will share different load, but in proportion to their ratings. Here we will see if we solve it without considering the limit, then what will happen? The droops are this 4% and 5%, and we can write these two equations. F naught minus F by 0 minus PA is equals to 0.04 F naught divided by minus 200. I hope you remember this, how we did this. The same no load frequency. These are the two generators, A and B. This is 200 megawatts and this is 300 megawatts. And now let us say we want to operate at this point, we don't know, PA and PB. Actually, in this case, the total load is 500. If we see, even if we see this diagram also, we can directly say, because the generation cannot go beyond 200 and for A, generator A, and for B it cannot go beyond 300. They will operate at 200 and 300 respectively. But the problem here, the question which was asked by the student was, so this will be PA if we respect the generation limit that we should respect, and this will be the PB. But if we do not respect the generation limit and directly apply this formula and try to calculate the ratio, then the ratio comes out to be 0.833, and the PA and PB values comes out to be 272.73. PA is 227 and PB is 272. So if we consider PA as 227, then what happens? That PA, the generation, the A generator is producing more than its maximum value, which is not possible. And generation B is okay, it is below its maximum value. So this is permissible, but this is not permissible. Without considering the limit, this question will become wrong. So whenever we calculate this P and PV value, we have to check whether they are within the limits. If any generator goes above its limit, then we set that generator to its maximum value 200, and the remaining load is transferred to the second generator. So this will become 500 minus 200, which is 300. Okay. Now what will happen? The question by that student was, what will be the operation, the frequency of operation? What will be that frequency? If we consider this auto operation point, so now we know the PA and no load frequency was 50 Hertz. This PA is also known. PA is 200. 200, 200 cancels out, and the frequency becomes F naught minus 0.04 F naught. This becomes 0.96 F naught, which is 0.96. So this will be for A. This is for generator B. Both should be same, but in this case they are different. But which is not possible. So 0.96 into this will become 48 Hertz as per generator A. FB becomes 4.05, and this change is happening because of different groups. This change in frequency is only because of different groups. Now this will become 47.5. But this is not possible that the two generators are operating in parallel at two different frequency. So in this case, if when they are having a different groups, we cannot say we cannot calculate frequency here, because in practice what happens is group is kept generally same. The group is in practice kept same so that frequency will remain same for both of them. If we see if the group is 0.5 for B also, then this will cancel out and we will directly get 2/3. That means PA, the limits are respected. So one option, so practically what is done is same group. Or otherwise, if you want to solve this problem, what can be done is consider PA operating at 200 megawatt and consider droop characteristics only for the second generator, which is PB. Okay. Then the frequency will become 47.5 hertz. So we have to take droop of only one generator in that case, because we cannot have two different frequencies. So that's why in this question frequency was not asked. So whenever you have to calculate this, always calculate the values of P and PP and check whether they are well below their max, whether they are satisfying their maximum generation limit or not. That is very important to check. Okay. So this was one important aspect to be covered, and we will see questions for week 12 also at the end. But this is a very important practical question, so please try to remember this. Okay, so here answer will be 2 by 3. Okay. Yes, this is a modified question which we had discussed. The actual question was, I think, this was 600, this was 200 and 400. So in assignment question, the PA maximum value was 200 megawatts. PB rating was 400 megawatts. And we had to calculate and the load was 600 megawatts. And then we had the droop was 4% and 5%. Droop for 4% and 5%. And we had to calculate the ratio of PV by PB. If you directly calculate this using this droop's value of PA, the ratio of PA, or the value of PA and PB, then you will again see that the PA will be more than the PVA max and PB will be less than PV max. So then we can make PA is equals to PA max, and then PB also here becomes equals to, because load minus PA is equals to PB max. So PB here is also PB max. The ratio becomes 200 by 400, which is 0.5, but we cannot comment on frequency here because of different groups. Okay, so answer here becomes 0.5. Okay, so we'll start with overview of week 12 now. In this week, very important points were discussed, which are the current topics we can say, or the future trend in the distribution system, or the power system in general and distribution system in particular. Because power system, you see, on the transmission side, there is already a lot of automation already existing. Because now earlier we had SCADA, but now we have VAMs based on PMUs. We have this timestamp at transmission level. We already have quite automation. Uh, so we have this wide area measurement system based upon EMUs, where we get the time-stamped phasors, or we call them synchrophasors. So these are time-stamped, and then we have location identification and isolation of transmission lines. We have the entire control center available here, where we can see everything, monitor each and every line, generators, and there are automatic generation control, automatic voltage regulator control. All these things are already, we have already seen this AGC, which is the primary control, and then we need a supplementary control. All this we have already seen. This is to make the error zero, final error zero, steady state error zero. Okay. This all these controller already they are inbuilt, and, and so transmission system we already have lot of automation, but in distribution system we don't have automation right now. The basic requirement for that is the smart meters, which still we are very far away from having smart meter and at for each and every consumer in Indian power system, distribution system at distribution level. We are very far away from that, and the smart meter is the basic requirement for advanced distribution management system, and it is a part of the metering, advanced metering infrastructure. And this facilitates bidirectional communication. So we can get real time data. The utility can get real time data from the consumers. Similarly, which can be used for a lot of analysis. And then similarly, the consumers can also get data for time of use tariff or real time pricing. Their prices are changing with each time block. So in India, we have a time block of each time block is of 15 minutes duration. So 1 hour we have 4 time blocks, 1 hour. In a day we have 96 time blocks. 24 hours. We have 96 time blocks. For each of the 96 time block, we can have a different price. But right now, what is happening? We have only a single price throughout the day, which is constant for the residential consumers. For residential consumers, we have a single tariff throughout the day. But for commercial consumers, they they have reactive penalty, also reactive power penalty for poor power factor. And they can have this time of use tariff. So it is that there will be a higher price for peak hours and lower price for the off peak hours. If we implement the real time pricing, let's say demand is like this, and the price also follows this, because if demand is high, the price is generally high, because the demand is high and generation might be lower at that time, especially in the night when we have renewables. Generation is less here, and demand is quite high. Prices can go high, and when the prices are high, the demand is also. If the consumer knows beforehand that the next time block the price will be high, or at least they have a forecast that next day the price is going to be a bit high in this time block, then they can schedule their demand in that way. Let's say the day next day, the utility announces, can announce a different time scales, but let's say the utility announces that this price on a day ahead basis. The next day, this will be priced for this time block. It's a forecast, not actual, because they also don't know. Or actually, even uh, in the evening, even the prices for day ahead market is revealed. So that also uh, they can publish. So if the consumer knows that the price is going to be high in this particular time block, which is evening hours, and generally, and in future we will see more number of EVs. EV penetration will be very high. And people generally, everyone is coming back from offices to home in the evening, and because EVs will be used, so they will be charging their EVs just after coming from the offices. And if everyone charges during that time, then because then demand will be very high and prices also can go very high. But if we know beforehand that the price will be very high, we can shift this charging if possible to other hours, maybe late evening. We can delay that, right? Because once reaching, after reaching home, we don't will go unless there is an emergency. Everyone will go out next day morning only. Instead of just by delaying the charging by 2-3 hours, we can save money. Okay, so we can save money. Other option can be people can charge their vehicles in the office parking. In future, the offices will also be providing the parking, the charging facility in the parking. So that can also be used during the day hours if the price is less at that time. Otherwise, generally in late in late evenings it is less, but it can be more also during late evenings. It is in. So if we know the pricing, the utility provides us that information, then we can plan accordingly. And this can really help the utility as well as the consumer. Consumer can save bills, and utility can also improve the voltage profile and manage the resources properly, adequately, and avoid load shedding, load curtailment. Okay, so this is possible with advanced distribution management system. These are difference between the traditional grid and the transformed grid. All of you, those who have attended the and gone through the recorded sessions for this week, you will find I'm just summarizing, or within 4 or 5 slides, I am summarizing the entire week content here. So this can be helpful for your revision uh, when you go through when before your exam. You can quickly go through these slides and revise the content. The traditional grid, they have manual. It's manual driven. It's manual operation. Manually, everything is done manually. We'll see fault isolation, identification. We see. I don't know whether you have observed this or not. In cities, it is not. It is very rare, uncommon because in cities, the distribution companies have a very huge responsibility that the load curtailment should be avoided at any cost, and 24/7 reliable power supply is a very important aspect in cities, especially in the big metro cities. We don't even realize that we see that the outages are not prolonged. They are very rare, and if it generally they happen only when there is some planned maintenance, and they will all announce it beforehand. But forced outages, unplanned outages are not that common in cities because of regular maintenance work which is going on. But if you go little away from cities to the remote places or the outskirts of cities or in villages or in towns, you will find that outages are prolonged. Even the forced outages are also very prolonged. One, because these feeders are very long, and then regular maintenance is not there. And they don't know about the status of each of the transformer because of very less often maintenance. And then because of long feeders, it becomes very difficult sometimes to locate the fault. I have observed, because we live in outskirts of city, so we find that when outages are there, especially when some storm is there or it's a rainy season, some short circuit has happened, a fault is there. Sometimes it happens that for 6-7 hours they are unable to even locate the fault. And sometimes consumer knows that there is a fault here, short circuit has happened, but they won't reveal it. It becomes very difficult for them to find out. So the fault identification, the location itself, the first step is, it takes so much time because everything is manual. In traditional distribution system, this is a very big problem, especially in the outskirts. So identification and location it takes a lot of time, and we need to rely on humans, manpower for that. So much manpower is required for all of that. And then so it is manual driven. The first is location, that is also manual. They will go on that van that they have, and FRT team, the fault, I think fault resolution team they have. They call it FRT. So that team will go and see everywhere. In each feeder, they will see where is the fault. So that is a very time-consuming process unless they directly know it from the consumer itself. Okay, then so there is identification, location, and then restoration is also manual. Sometimes what happens is they are trying to restore it, but there is some fault at the substation level. It happens many a times, especially in villages and towns. then again they have to do it. There is no optimization at all in traditional grid. We cannot say at all. There are some optimization, but those are approximations based upon their experiences. They do it, but there is no formal optimization as such in distribution system as of now. In most of the distribution, we can say, because we have seen some case studies like in the Noida and Delhi where the distribution ADMS is already existing. It is the Delhi is the first city where means where the advanced distribution management system is there by Tata Power. So otherwise, most of the distribution they don't have this kind of optimization, formal optimization. And because we don't have smart meters, we don't have operational visibility. We don't know what is happening because there is no communication with the consumer. The meter reading is also manual. The person will go, one of the employee of the utility will go there and he will read the meter and give you the bill. But that is also the meter reading is also manual. Once we have the smart meter, this job will be finished. They will not be required. No need for manual reading. We can directly get the uh, consumption pattern as well as actual consumption of the consumer at the center of the communication channel. And then there is improper demand planning because we don't have this operational visibility. We don't know the actual uh, what is the actual demand, and also there is theft, especially in towns and villages. So that demand planning is also not that proper because of lack of data, and then improper topology processing also. This is also done based upon their experience. One example you will see, very common example in India, especially in villages, is agricultural feeder. There are rural feeders and urban feeders. There are some substation which cater to two different kind of loads or feeders, rather. So substation, there are certain substation which are at the border of a town or a village, right? So they have even city and a village also, border of city and a village. So they will have urban feeders and they will have a rural feeder. They will have or means there can be several rural feeders also. So in that case, they have their operation is different. For urban feeders, they have to supply. They try to supply 24/7, three-phase supply, all the three phases. But here, because rural load is also less, and they are not that given that priority. Urban load is given more priority, so load shedding is avoided in urban feeders. And rural feeders, load shedding is the last resort in urban feeders, but in rural feeders, nowadays it has improved, but still load curtailment is there. So whenever load curtailment is needs to be done, they will do it for the rural feeder, not for the urban feeder. If nothing is working, then they will do the curtailment for both of them. But first they will do the load curtailment for the rural feeders. So here, what do they do? They have created three slots, 8 hour each, 8 hours, 8 hours, 8 hours, and they will. If let's say there are three feeders, one, two, three feeders. So this first feeder, it will get the three-phase power supply for let's say 1 to morning, 1 to late evening we say, morning 1 to 8, 00 to 08 hours we say. Say 00 to 08 hours. So you would have seen that these flour mills in the shop, they operate on three phase. They have three phase induction motors. So they will, if there is a shop in that feeder, which is getting supply from that feeder, connected to that feeder, then it will have to do its operation in the morning hours 6 to 8. Okay. Then the second feeder will be 9 to 9 plus again 9, 8 hours. 9 to 5, and this the rest will be here from 6 to, sorry, let me write it as 09 to 10, 17 hours. This will be 18 to 00. Okay. This should be 3 plus, sorry. Okay. Sorry. This should be 15 and 16 to 24 hours. Okay. This is 0 to 7, I can say 8 to 15 and 16 to 24 or 20. Okay. Okay. Yes. So this is based upon, this is all manual and it's a simplistic approach. But this can be made more effective by using optimization techniques, by bringing in automation, and which can even improve the benefits for the consumers. This is what we call it as a rule-based strategy. So it's a simple rule-based strategy where they have created a rule that the feeders will be alternately supplied this three-phase power for 8 hours in continuation. But this can be made more efficient based upon optimization technique frameworks, and that is the objective that is performed in the advanced distribution management system by using different techniques, optimization techniques, because there is more visibility. We know the actual pattern, demand pattern. We have historical data of the pattern, demand pattern that can be exploited to make good decisions, informed decisions, and to take even proactive decisions. Okay. So here the difference is we have a system-driven distribution, system management, and optimization. Here the restoration is automatic, not manual. So for that we will need different kind of switches which can receive signal, which can tell the utility that there is a fault here, and not and the system will do isolation and everything, and then even later automatically close it. So here optimization is done to improve the performance of distribution grid, because we have good bidirectional communication, we have access to the actual real-time data, we have operational visibility of both the load pattern, load demand, as well as the network topology. One thing I forgot to mention that Earlier, now this was distribution grid. Now also we have distribution grid, but we have added one term here, active. It means earlier the distribution grid was passive. Yes, because we see the earlier distribution grid, now it is literally changing, but not that much. Still, the active part is very less right now. Very, very small. That is minuscule, but earlier, before the renewables were there, even few years back, up to few years ago, then we can see that the distribution grid was only consuming power. It was only consuming power. There was no injection or generation at the distribution level. There was only consumption. Generation was at sub-transmission and transmission level. But now, because of this distributed generation, we have generation at even the primary consumer level, secondary consumer level, sub-transmission, everywhere. So now the consumers have become prosumers. Production plus consumption, prosumer. Consumer, producer plus consumer becomes prosumer. Yeah, I think you would know this. So it is producer of power and consumer of power. So this is pro and prosumer. It becomes prosumer. Because now homes they have solar panels, solar PV plants. Now they are companies are also providing small wind turbines also, which can be placed at the rooftop and they can generate electricity, especially in areas where the quality of wind resource is good, wind speeds are high. There, it is very beneficial. So these are rooftop. If they are grid connected, then they can supply to the grid also. Yeah. Even if they are not grid connected, they are impacting the demand pattern. They are changing the demand pattern. They are reducing the net demand required, the net demand of the consumer, even if they are not grid feeding or grid tied, then they are altering the pattern, demand pattern. Another is the behind the meter battery storage. They have a storage at home, then electric vehicles, then new technology like peer-to-peer trading. A consumer, two houses nearby, a neighboring houses, they can exchange power. If this is surplus, sorry, yeah. If it is surplus and it is deficit, then power can be transferred from here to here to this house 1 to house 2 and vice versa. So this can also be this is so all these things are changing the demand pattern, altering the demand pattern. Unless we have these smart meters, we will not be able to know all these things. It is because these are invisible to the utility. Their behavior is not known. So all these things are changing the dynamics of distribution system and which requires a lot of upgradation, optimization and communication. Okay, so now, yeah, I have told this also that we can have predictive simulation and automation operation. So this will also help in intelligent load shedding, not a rule based. Then centralized operation is there and the future will be unmanned substation, everything will be automatic. Only when that automation fails, the manual intervention will be required. Then we have bidirectional communication. This we already discussed. And field crew management can also be optimized. Now see, this is the advanced distribution system in a nutshell, we can say. I have written here, these are the drivers for advanced distribution system. We have discussed some of them. We want a resilient distribution system. Resiliency means if there is an event, some fault or something, natural disaster because of which there is a disruption in power supply, then how quick, how fast the distribution system is able to cope up with it and again restore the supply of power to the consumers. That is part of resiliency. And because of the extreme increasing extreme weather events, this is becoming more and more important. And also if the infrastructure is aging infrastructure, then also it becomes a challenge. Resiliency, because in that case the equipment needs to be changed, and the consumer may have to wait uh, for even one day. Sometimes it has happened. So I have seen that when, especially in these rural feeders, what happens that if a transform, because that they are not regularly monitoring everything, all the equipments, especially the transformers. So if they are not monitoring, and if the transformer is aging and they are not keeping a track of it, and because of overloading or something, gradually it ages reducing, and one day it completely goes out of service. Then because they have not kept a track of it, suddenly if it goes out of service, the consumer will face a prolonged outage. And the consumer might have to even wait for 1 or 2 days, and it becomes very difficult for the consumer. Sometimes it happens that the uh, consumer knows that the transformer is about to it's in a critical condition. It can cease operation any moment. So the consumer, because consumer has faced outages because of the transformer faults, then consumer can approach the utility that I want to please change the transformer, but they have this bureaucracy, long procedures. You have to write application, then it will be forwarded. They will make an order. Then you have to call the FRT team, and they will take 1 or 2 days. And it takes a lot of time. So ultimately, the consumer has to face the problem when the regular maintenance and monitoring of equipment is not done. But all these things can be overcome when we have meters at each and every, because they already have meters. Transformers also have meters, but they don't have communication facility. They do not communicate. So if all these meters are smart, then it becomes automatically we can see we can see the health of the transformer oil, that's lubrication, it's any kind of fault is seen, but analytics can be developed to predict any kind of dielectric breakdown or of the oil. All these things can be done if we have the data. Okay. Then we have seen renewables also. Integration of renewable is changing the demand pattern that is not visible, that makes them invisible. And that is also required. For that also we need this advanced distribution management system. Then replacement, this also we have seen the equipment. Replacing the equipment is also a challenge in the existing distribution management system. Then safety of the crew member. This is it's a concern because when system are not, and because right now they have to uh, restore, or even first of all isolate the faulty section and then restoration and isolation. In that case, sometimes because of mishandling or some errors, human errors, people, those who are doing this manual isolation and restoration, they have to lose their life because of human errors. So all these things we can avoid if we have automation. Then functions, these are 5 functions of the distribution system, advanced distribution management system. First is modeling. Then first thing is you have to model the distribution system, and we can we have to model each and everything, entire distribution system, each and every component, in that too entire three-phase detailed model, because we have single phase loads also, two-phase loads and three-phase loads also. Unbalance is a inherent aspect of distribution system. Then after modeling, once the model is there, we analyze the system, we do state estimation, power flow analysis, fault calculation, reliability analysis. This is then only once we have the model with us. And then once we have modeled the results, we can monitor the power flow on each of the lines. What is the status of transformers, overloading of the equipment, all these things can be done. So the data can be fetched from the remote equipments to the control center, and then it can be analyzed and alarms can be raised, reports can be generated, and the trends in different demand patterns, as well as the aging trend in aging of equipments and the degradation of their life or SOC, different, all these things can be monitored. And then operation, in operational aspect also we can do fault management, switch management, and intelligent load shedding. Using this, the monitoring and analysis we have done using the model. Then this is operational aspect, and but we can optimize this operation also by doing different, all these things, by using the volt for optimization, network reconfiguration, short-term load forecasting, and demand response. Okay, so short-term load, if the load forecasting is model is quite good, then it becomes very helpful for the utility to meet the demand, because the utility has to plan its portfolio. It has to optimally utilize its portfolio, because utility wants to minimize the operational cost, minimize the cost of procurement. And the utility has different sources from where it can procure electricity, can procure energy. There are generators, different generators. There are central generators, if we talk about India, which are owned by NTPC, owned and operated by NTPC. Then we have these intrastate generators, which can be by independent power producers or can be by the state-owned utility, like the the state generation companies. So all these generators are there. Then there can be even interstate IPPs, interstate independent power producer also. This is especially there when for renewables. A renewable plant is there. Let's say we are in Maharashtra. We are in right now. I'm in Mumbai. So Maharashtra State Electricity Distribution Company Limited (MSEDCL), they can have a contract with a renewable plant sitting somewhere in Tamil Nadu or Assam, anywhere. So that it's a part of interstate generator and it is independent. It can be state on. Generally, it is most of these are private, independent power producer owned. So they can have contact with them. So these are the generators, and then there is market also. Market also there are different market operates at different time scale. We have day ahead market, real time market, we have term ahead market. So many types of markets are there. So many options are there. The point is that the discom, the distribution company has so many operations. So you see in generators also there are so many options, and in market also based on different time scales they have different options. How much to procure from day ahead market, how much to procure from real time market, because we don't even know the price of the market. So how much, what will be, how much, let's say medicine should be such that it is more, it is economical as well as reliably we can meet the demand also. Suppose one, if the price in generally the price in India, we see price in RTM real time market is lesser than day ahead market because no more, because it's uncertain. No one wants to take the risk that I will not be able to get power from the real time market. So they try to uh, have bid as high as possible in the day ahead market, because in day ahead market there is a price cap of 10 rupees per megawatt, or 10 rupees per kilowatt hour, 10 rupees per unit. They have a price cap. So they will try to bid as high as possible, especially during the peak demand hours, so that they get enough market requirement from the market. And the remaining is done in the RTM. Now, what should be this ratio? That is, they do it based upon their experience, but we can make it, optimize it by using different optimization techniques, and we call it as portfolio optimization for discounts. All these things can be done. In demand response, we can also do uh, reduce the peak demand by incentivizing the consumers, or by incentivizing them to change their demand pattern or shift the demand from one time block to the another, so that peak demand can be reduced. All these things can be done. And the portfolio optimization and demand response, for them, one of the important tool which is required, or input from a tool required, is the short-term load forecasting. So we need to predict the load in advance to take decisions. That that so that load forecasting models need to improve. You can have different types of models. Even network reconfiguration can be done to reduce the network losses. And to even quickly isolate the fault and quickly restore the power by doing network reconfiguration. Can be done to increase the reliability. It can be used to increase the reliability, to reduce the network losses. Okay, so architecture, so ADMS will contain so many these things. SCADA is required for data acquisition and control, supervisory control. Then management system, which has all these things. Then distribution management system, this is outage management system, this mobilization of work crew members and work management, and then visual reporting, which is part of this monitoring. Monitoring is done. Right. Keep on monitoring and also we can visualize it. So we can keep a track of everything on a real-time basis. Then technology and trends. So most important is EMI, advanced metering infrastructure. And smart meter is its backbone. And MDMS is the meter data management system. Cybersecurity, because so many, everything we are trying to, the data which we are fetching, everything we are trying to communicate over a distance. So there can be time lag also. And purposely one can inject certain time delays or a spurious data, can alter the data. Because there are different types of cyber attacks. One is false data injection, eavesdropping, and so all these things are there. And once everything becomes so automatic, then the challenge of cybersecurity also becomes very prominent. It becomes an important concern, a very important criteria for designing the we say cyber resilient advanced distribution management system. All these things are very important. And we have also talked about the data. We have talked so much about data. We require so much data. So how can we use that data? So different AI techniques and big data analytics, all these things can be used to help us make good decisions, analyze the data better in a better way, and use it the further processed data for optimization. Now you might say that okay, these are new technology, but what about ancillary service? It is not a new technology. Ancillary services provisions are already there on the transmission system, but for distribution system we don't have this. So it's a trend. It's a trend and new trend in the distribution system where we can have even ancillary services provisions. We can procure ancillary service entire the distribution management system. The one thing can be one component can be ancillary service management. So even there are now talks. Even one report was there for if were jointly developed by IIT Kanpur, IIT Delhi, and one government organization. I think Delhi. I don't remember that, but they have published one report on the need of distribution system operator. We have transmission system operator, but we don't have distribution system operator. Now, distribution system operator, they will do so many functions, and so then this then we can have all these things. Ancillary services provision and everything can be done. The next technology is blockchain also for peer-to-peer trading. It can be used. So we have seen here optimization. First one was volt-var optimization. So here volt-var optimization, then it's a multi-objective optimization problem. So generally we have seen that this is a standard form, right? Minimize f of x, where x is a decision variable and subject to some constraint. Okay. So here we have a single objective, but here we are talking about a multi-objective. So we have, let's say decision variable is still x, but we have two conflicting objectives. That means increasing one decreases a second, and vice versa. Here we can see one objective is active loss minimization and load demand reduction. So we see if demand increases, the loss will increase, right? So if you want to reduce demand and we want to reduce loss also, both we want to reduce. So how to do that simultaneously? We want to minimize the both. We want to minimize load as well as losses. So we can give weights. They can be weighted. Weighted sum is used generally. If you want to give more weight to one thing and less weight to another, then let's say if this is f1 plus 0.3 f2. So the solution will try to make such the solution will be such that it will try to minimize the loss first. It will give more importance to loss minimization than in comparison to the loss, the demand minimization or demand reduction. So here we are minimizing weighted sum of two objective functions with respect to certain constraints. Here here controls or you can say these are the decision. These are giving us information about decision variables. So their variables will be the decision variables. Capacitor banks, so we will be having taps, number of taps as is. One variable will be tap position. It is an integer variable. Those taps are integer. Okay. Some integer 16 or 32 taps. So these are integer values. Then OLTC. No, sorry, this was capacitor bank. OLTC have taps. Capacitor banks also you can have different combination of capacitor that is also integer. Number of capacitors in the capacitor bank to be used. Then voltage regulator we have. And smart inverters also. These are the controls. We'll be having decision variables associated with them. And constraints are the number of taps in capacitor bank operation. We want to limit, we don't want very frequent change in taps of voltage or capacitor bank because that will reduce the life of these equipments. Then inverters operational limit, they have some limit of active and reactive power which they can supply and all these things. Then they have rate also, fault rate capability, all those things. Then voltage magnitude across the feeder, we want to be within a range, we want to minimize the voltage regulation also. And then what is the storage and the SOC of storage? We want to keep it within some band 0.2 to 0.9 to avoid degradation of battery. Okay, then we have different levels of automation. These are levels for automation: process level, bay level, and substation level. In process level, we have this gas insulated or air insulated switchgear. This circuit breakers, SF6 based circuit breaker, instrument transformers. Here we have current transformer and potential transformer, CTPT. and we have power transformers, surge arresters. Sorry. And then at bay level, we have these functions like protection, control, monitoring, interlocking, and data acquisition. Then third is this automation, fault evaluation, event and alarm viewing and acknowledgement, and remote communication for telecontrol and supervision. Now moving on to the another function of this ADMS is this, can say this fault management. It will come in fault management. Fault identification, isolation, fault location, isolation, and service restoration. These are the three things which are done here. Here the objective is to reduce the outage time to the end consumer, correct? Then distribution automation application. We want to minimize the number of overloaded elements. We want to minimize the network loss, and we also want to minimize the average voltage. All this are the objective of this fault location, isolation, and service restoration. The steps involved in this fault in this is a short form for this fault location, identity, isolation, and service restoration. Steps involved are first of all fault location and the time of fault is determined, and then second is isolation, fault isolation for multiple fault location. Then third is, because now third these two are involved for this service restoration. We want to optimize the service restoration strategy. And the last is the results of new switching positions. What are the new switching positions? And what is the overall network impact? That is observed. And there are three architectures for this. One is centralized, which require, because it is centralized, it will require a lot of communication. Communication requirement is quite high. High bandwidth communication is required here. And because it is centralized, if there is a problem in that communication challenge, then entire control is lost. So from reliability perspective, it is not considered, or we can say recommended, but because cost wise it might be effective, so sometimes we use it, but it is not that reliable. And also so much communication requirement is there. Then decentralized and distributed are also there. The distributed here, they will, for each equipment we have this communication systems, and each equipment can even coordinate and share information with each other, and then based on that they can take some decision. The algorithm, the utility can do that. Since we are talking about automation, then we have standards for automation for substation. We have IEC 61850 standard for subsystem automation. Sorry, substation automation. So this is standard for subsystem automation. Substation automation. It is a standard for communication networks and system in substation for power utility automation. It specifies the expendable data model and services. It supports free allocation of functions to devices and feature development of functions. It also provides the substation configuration language, which is used to do all the processes to carry out all the tasks of substation, how these different equipments can communicate with each other, and then it uses Ethernet and TCP/IP for communication. Then goal is interoperability, where it is possible to exchange information between devices of different manufacturers. They should be able to communicate with each other. Then free configuration. Although there are different philosophies, still one should not debate, right? And there should be options available for centralized, decentralized, or distributed. So these are the different operational philosophies. The device should have that ability to configure itself, irrespective of the operation philosophy. And long-term stability. So this is for future proofing. So if the communication technology evolves, the standard also needs to evolve. Now moving on to the electric vehicle part. This is very interesting. You'll see. I think it would be almost everything is covered in all these slides. Electric vehicle, we'll see only 3 slides are there, then we will take questions. Here, first of all, what is the need for electric vehicle? All of you already know this. We want to reduce the carbon footprint. It helps us reduce carbon footprint. It helps us reduce our dependency on fossil fuels because India is a net importer of coal as well as what we call that petroleum products, which is used massively used, excessively used in transport sector. We are highly dependent on the availability of crude oil from other countries. Processing is done within India, but the crude oil is purchased from outside. And geopolitics certainly impacts that. Then we want to reduce the peak demands. For that, also electric vehicle can help us, and it can also provide the provision for ancillary services. What are benefits? Benefits are that there are no moving parts in electric vehicle. Mechanical parts are very less. Maintenance cost is very less. Then there is zero tailpipe emission cost. No tailpipe emission. Then we have tax and financial benefits. At least now, for a few years, we do have under the FAME objective fast adoption and mobility of electric vehicles. Then it is easy to drive because there is no suspension here. It is easy to drive because there is no suspension system. I will say there is no gear. There are only so there is no clutch here. So it's very easy to drive. Anyone can learn it very easily. Within just you need few days for steering control. Then you can easily drive it. Then no noise pollution. Here I will say one thing that some people have this concern that they want they don't like EV because they have no noise. They don't produce any kind of noise. They feel good when they hear the noise of the car engine of the car or the bike, you'll see that many people they have this Royal Enfield or these kind of bullet bikes. Here they purposely add these this what we call burst noise burst. So they will do it, make noise, but that is noise pollution. But still, certain people they have that inclination to hear the voice of the engine. Some people say that because the EV is very silent, it's difficult to know that electric vehicle is coming from behind. So people become more prone to uh, accident as per them. But we have horn, right? We can use, so that's not a problem. Yes, but these are very silent uh, vehicles. So these are the benefits. Then types, we have hybrid electric vehicle where we have both a small motor is there. So it's a combi. It has two fuels. It has a small battery and motor also, and it has an engine also. So two kinds of fuel are there here, and it is used. But it cannot. That battery cannot be charged. That battery is charged using that gasoline engine only, and it can be used in time of when acceleration is required. So this battery is only to support it, the electric vehicle, the gasoline engine. Okay. Then plug-in hybrid electric vehicle. Here it's here we can charge it. It's a dual fuel, dual traction. Okay. Hybrid we cannot charge it. It is charged through the gasoline, but here we can charge it. So here you cannot operate it only on electric using battery. The range is very limited. But here you will find you can use battery alone also. Or although the range is less, it is you can use it, can charge it and use it. So both it's a dual fuel, dual traction. And battery electric vehicle exclusively battery. Exclusive battery. And this is the fuel cell electric vehicle. So we have inside the hydrogen and oxygen are combined to produce electricity and water. And that electricity is used to rotate the motor, to run the motor. Then we have batteries, different types of batteries. These are the available batteries, but out of these, lithium ion is most widely used because of its high energy density as compared to others, and many other advantages also. Its degradation is low, self degradation is less. Lead acid battery, the life cycle, its life is very less. Similarly, nickel cadmium, we have that what we call it, that memory effect. So that is a disadvantage of nickel cadmium. And lithium ion, although it is advantageous over these three batteries, but the problem is for India is that the lithium is very costly because we don't have any reserve. Neither we have reserve nor we have processing facility. So we are heavily dependent upon imports from other countries. That increases the cost of the battery. So alternative to those lithium ion batteries, this are these redox flow batteries, sodium sulfur batteries. lithium sulfur batteries and lithium ion batteries. And this is little is safety concern is there. So these are the other alternatives which can be used. Then there are different factors which affect the charging. So if battery size is large, then the charging time will be more. Similarly, if you're charging at a higher SOC, then charging time is less. If I am charging at if the battery has 10% SOC, then if I charge it, it will take more time. Then charging rate. Charging rate can be for vehicle also and for charging point. If the charging rate of vehicle is quite so charging rate of the charge let's say the charger is a fast charger, but the vehicle battery doesn't support that high rate of charging, then you cannot charge the vehicle in with that high charging rate, and then time will be you cannot reduce the time of charging in that case. Similarly, the vehicle might be having a battery which supports fast charging, but the charging point might not be a fast charging. Then also that is a incompatibility. Right? So in that case, also the charging rate will be limited by the charging rate of the charging will be limited by the charging rate of the charging point. In temperature, it's difficult to charge at lower temperatures than hour of the day. If peak demand is there and we are charging at the time, then the energy available might be less, so we may not be able to charge it. If more number of EVs are there, then also there is a problem, because if in one electric vehicle charger there are several EVs connected, then it can reduce the share of each of the EVs. Because they are sharing power and that much power may not be available, so the time reduces. Then type of charging cable also impact that whether it is type 1, type 2, CHAdeMO, or these different types of charging cables are there. They also have a limit on charging. Then battery drain out and battery idling. If we have kept battery for a long time, then it is its life reduces. It battery drain out also is a problem related to battery, where we have problem that the battery has drained out because of excessive because of degradation. It happens because of degradation, let's say. Because of degradation, the health of the battery has reduced, so it will not be able to discharge for a longer duration. Okay, it will discharge in a very less time as compared to its original discharge time. Then we have different types of charging. We will see this using a picture also. We have onboard chargers, we have offboard chargers, which are fast chargers, and then we have this solar powered electric vehicle supply equipments. Then we have this wireless charging. And last one is the dynamic charging. Here the roads are made such that they support the dynamic charging. The vehicle, while cruising on the road, it can charge dynamically. Then the impact of electric vehicles. Okay, we are trying to integrate electric vehicles, and it will be integrated at a very fast pace. As soon as the charging, this EV electrical uh, supply equipment, uh, its network or its availability becomes, there is a good availability of electric vehicle chargers, then the rate will further, the EV penetration will increase even further at a faster rate. And that will have a impact on distribution system. So it will impact the power quality. It can be under voltage when large scale EV charging is happening. Then there are unbalanced because we have these different number of chargers, level 1, level 2 charger and fast charger, and they can be distributed over different phases. Certainly it will lead to unbalance. Then there can be DC offset because of the voltage and current harmonics. And frequency switching, the frequent switching on OLTC, if there is a under voltage and over voltage problem, then there will be frequent switching off. This should be off. I will discard everything. This should be off, not on. The frequent switching of OLTC. For this, due to heavy voltage drop by EV charging, there can be this frequent switching and which can degrade the life of OLTC. Then phantom loading, even when there is no electric vehicle connected to the charger, it draws some power. That is called phantom loading. It comes from this in biology. There is a term called phantom limb. So we call in some persons their hand is cut due to some injury, but still they feel that their hand is there. So that is the phantom loading. Although hand is cut, but if you try to do something, although hand is not here, if you try to do something like this, so they will feel that my hand is there. So although it is not there, it is drawing some power. Then transformer can become overloaded due to strain, and then it can result in premature aging and potential failures. Capacitors, the harmonic introduced by these non-linear loads, they can result in resonance with nearby capacitor. And these harmonics will result in additional heating, leading to copper loss. And then there can be premature operation of fuses due to copper loss by harmonics. And they also have negative impact on the operation of protective elements. Harmonics are creating a lot of problems. Here we see, first we have these three level of electric vehicle chargers. Level 1 is 230 volts. In India we have 230 volts, which is the power level here. This is power level, and these are the voltage level. So at 230 level, the power is voltage level. The power is less than 1.8 kilowatt. At 400 volts, this is a three phase. It is less than 19.2 kilowatts. So this is single phase. This is three phase. We can use a normal residential socket, and this will be your power socket. And then we can have it line to line voltage can also be used. Then 400 volt DC, this is the fast chargers. DC fast chargers. These two are AC, and this is DC fast charger here. 50 kilowatt to 150 kilowatt. Sorry. Now here we see we have these two. One is DC charging system power flow and AC charging system power flow. This is for level 1 and level 2 charging system, and this is DC1 is for the DC, this level 3 charging system, which is DC fast chargers. And this uses the off-board chargers. Why can't we have large, big off-board chargers on the vehicle? These on-board chargers, their rating is small. Their rating is small. Because if we have a big off-board charger, then that will increase the weight of the car, that will also increase the cost of the car. So we want to have an optimal onboard charger, not too big, not too small. And then if you want to charge it quickly, then the DC fast charger, which is the off-board charger, can be used. And for this, the battery technology, the battery chemistry should support. Should support higher C rates. So 1C, the C rates, 1C implies that the battery will be charged in 1 hour. So 10C means it will charge within 6 minutes. Right now we have batteries like 2C or 0.3C, they take 2 hours. Still for two-wheelers even. 0.2C, it will charge at its rated capacity within 2 hours. But if the charger capacity is small, then it will take even more time. So the capacity of charger, the onboard charger is uh, very important here. So here we can see this is the grid, our grid. Then here this is the car model. We are charging it through this electric vehicle supply equipment, and the inside view is shown here. So this is a grid. Then this is connected to grid, and so from grid we are getting AC power, which is going to the electric vehicle supply equipment. From here we have one communication wire, which is the pilot wire between the onboard charger and the EVSC, which will give the pre-connection signaling, and the co-pilot gives the post-connection signaling. Okay, so this from here, this EVSC will also give an AC supply. The AC supply will go to the AC-DC converter, which is the onboard charger is an AC-DC converter, and then it will convert the AC into DC, and it will charge the battery pack. Okay. So this is therefore level 1 and level 2. So for using the same electric vehicle, charging it from level 1 and level 2, this charger should support this 19.2 kilowatt. At least it should be rated at 19.2, because if it is rated smaller, maybe 7 kilowatt or so, then it will take more time. To exploit this level 2, it will have to be higher rating onboard charging. And this is the DC charging, fast charging using the output charger. Here we have grid. Grid is giving AC. Then we have supply equipment plus the AC-DC converter, which converted it into HVDC. Then it is used to charge the battery directly. Here onboard charger is not used. So we directly the DC charger is used to charge the battery. Okay, this is a link from where I have taken this picture. You can also download if you want. Now let us move to the question parts here. We are left with 20 minutes. We'll see the questions here. Okay. So first question is this, and because next all the 5 questions are based upon this question itself. This data. It's like 4 questions, 3 or 4 questions are based on this data. The next 2 questions will be having different data. So here it's a very simple question. All these questions are very simple. So first is the data, the given data says that the load demand is 500 megawatt, sorry, 500 kilowatt at a power factor of 0.90 lag. Then the feeder length of the feeder, length of the feeder is 4.5 kilometers, and the line impedance Z L is equals to 0.14 ohm per kilometer. Okay, voltage at substation is 13.5 kV RMS, and transformer impedance, which will not required here as such, is also given. And we want to calculate the total load current. Okay. It is something means here we have a transformer, here we have a line, and then here we have a load. This is the load. It is, so we have this load current. Same current is flowing here, and we have voltage here. This is Vs angle 0. This is some, this voltage will be some VR angle delta something. Okay, so this current which is drawn, it depends upon this switching and voltage, but we don't know that because we don't know the current. It's an iterative process. If you want to solve it, you can solve it iteratively. Assume some value, then we can converge into one or two iterations. But here to simplify the analysis, we are directly considering this Vs only. We are calculating the current using this value, the substation value, because you will see, let's say if you find the current here, let us assume that VR is equals to 1, okay, 1 angle delta. Okay, and Vs we know it is 13.5 kV angle 0 kV RMS. Okay, now we'll first calculate IL using this VR, some 1 per unit, and this is also, let's say, 1 per unit. If I calculate IL using this 1 per unit, I will get some value, you know. If I substitute that value and if I calculate Vs, then Vs will be more than 1. Right? But it is not actually 1, but its actual value is 1. So this difference we can know the error. Based upon that error, we can fix this value at 1 and use that current value to calculate this value. And using that, calculate current, and then again keep on doing it, and then you can converge. Finally, you'll find the, but here actual value, this is actually done forward, backward sweep methods are used. But here we are directly calculating IL using the substation voltage itself. So you know the load apparent power divided by voltage. Take magnitude and you directly get the current value. So here the apparent power demanded by the load is 500 divided by 0.9 kVA divided by voltage, which is 13.5 kV, and you will get your answer of current magnitude. How much is this? 500 divided by 0.9 and divided by 13.5. So it comes out to be 51.15 amperes. So this is, yeah. Okay, the answer is this. Let's see what is the next part. The next part is this. Yeah, this is done. The next part is voltage at the load end. Yeah, now we use this. Yes, see what we are doing here. No? I told you in first part, we said that we have a voltage source here. We have a transformer here, which also has some impedance, 7.5% on MVA base. We have this line impedance also. Then we have 8 VR. And we have load here. Okay. So we said that in first question we said that this is equals to Vs angle 0. If we consider this as Vs and this also Vs, then it means the current here is 0. No drop here. The first question we have assumed that whatever voltage is at substation, same thing is at here, at the load end also. But now we are saying use that current which you have calculated to find out the this value. Or in one sense, we can also say like this, that I want this load voltage to be same as source voltage equals to substation voltage, and to ensure that VR is this, I will have to increase the VS source voltage. In that case, it will be some 13.5 plus some delta V. Okay. So now here, if we assume the current we have calculated and if we assume substation voltage is 13.5, then what will be the this receiving end voltage at the load end? So we have to subtract the impedance in that case. So here actually we should subtract the overall impedance, this line impedance as well as the transformer impedance. But if we neglect this, because it is very less, it is 7.5% only. It's only 0.0755. If we neglect the transformer impedance, we can get an approximate value for the voltage drop. We can consider this transfer impedance also to calculate the actual voltage loss. But since we have calculated the current here also approximately, we are neglecting here the transformer impedance. But if we include it, then the value will be less. There will be more voltage drop. So here the voltage drop due to line impedance will be delta V is equals to I into Z. So I is 41.1, what was that? 15 multiplied by 7, sorry, not 7.14 ohms into 4.5 length. Then you will find that its value is something which is this 41.15 multiplied by 0.14 multiplied by 4.5. It is 25.92 volts, which is the voltage at receiving end will be 13.5 minus this value. It will be 13.47. Okay. Then we can calculate the regulation also. Voltage regulation. Voltage no load minus voltage full load divided by voltage no load, which is substation voltage minus receiving end voltage divided by substation voltage. This is 13.5 minus 13.47 divided by 13.47 multiplied by 100. We'll get 0.192%. This is the voltage regulation. We want the voltage regulation to be as low as possible. And this is also done. Now calculate the power loss in the distribution field. The power loss is I square into impedance. I square is 41.15 S square. It is called in watt per kilometer. So here we use 0.14. This is in ohm per kilometer. You will get the value as I think 236%. What is this? 41.15. 237. Now this is the next question. So this next question says we have total load of 3 megawatt. Total load PF is 0.87 lakh. Desired PF is 0.96 lakh. We want to improve the PF. For that we use capacitor, and we have capacitor available of rating 165 kVAr. And we want to find out what is the extra reactive power in megavolt ampere reactive to be supplied by the capacitor when connected to the load side to achieve the desired power factor. So here you see I have already calculated. Here you can see this is a power triangle because here we want to increase the power factor. So here active power remains same. Q we want to Q which is absorbed by the load that we want to reduce, because we want to supply it using the capacitor. So the overall capacity, the power factor and the load end will reduce. Okay, so it will improve, power factor will improve. Okay, so initially it was Q1. So this bigger triangle is the initial triangle, big triangle. Here we shows P and Q1. P is 3 and Q1 is P10 5. P10 5. You can say this is P10 phi 1. You can write it as P10 of cos inverse phi 1. Okay, you will find this value as 1.7. Similarly, you can find Q2 also, which is P into tan of cos inverse phi 2. And this comes out to be 0.875. So this is Q2. Now if we subtract these two, Q1 minus Q2, then we will get how much power should be supplied by the capacitor, right? So easy, very simple, right? So here we can easily know. So here we have already calculated Q1 is 1.7 and Q2 is 0.875, and difference comes out to be 0.825. So this much MVAR is extra required to be supplied by the capacitor bank. Capacitor bank. In capacitor bank, there are several capacitors connected in parallel. And it is given that one capacitor is having a rating of 165 kVAR. And the next question is how many capacitors are required? This is also very easy, right? So this is 825 kVAR total Q requirement, and Q supplied by one capacitor is 165 kVAR. So number of capacitors is equals to total QC divided by QC per capacitor. Right? So this will be 825 divided by 165, and this is equals to 5, right? 5 capacitors. So we need 5 capacitors here. So next question is, which protocol is used for communication networks and systems in substation for our utility automation? This we have already seen, right? What do we need? Which this 61850 IEC is for substation automation protocol. This one is for DER interconnection of DER. 2800 is for transmission level DER integration. And this is for synchrophasors. Select the isolated inverters. Which one? Buck, boost. These are non-isolated. And non-isolated, we can have a limited gain also. Get a gain more than 4. And beyond that, we need to use isolated. So this is dual active bridge, flyback, and push-pull. These are isolated converters. So these are the questions for today. Thank you for joining today's session. We will meet on Saturday for the last wind-up session. Thank you, all of you.